We left off with this lesson in Inventum, Unit 9, using counting techniques to determine probabilities. The main takeaways are the permutations, combinations, and when to use those. I wanted to do some of the more complicated problems with you today, and then we'll stop and give you time from 9:30, or I'm sorry, 10:30 to 11 to work on the mastery test. And then I have all the problems ready to go if you need to ask about them while you were doing it. Tomorrow we'll start the new lesson. I just realized what I left at my desk is my writing pen. So I'm going to step out of the room. I'll be right back and do a quick review together and then do some of the more complicated questions from the mastery test. One moment.
And then just keep it up and see, hopefully she'll respond to you. Okay?
All right. Before I get going on this, can you guys hear me okay? Aaron, Antonio, Andrew, can you guys hear me? Yes. Okay. Thanks, Aaron. So let's do a quick review on permutations, combinations, the fundamental counting principle, and then some questions to practice. Thanks, Antonio. Here we go. So, first off, the fundamental counting principle. Good morning, Bailey. So, good morning. Glad you made it. The fundamental counting principle. This is the rule that says we multiply together all the different ways there are to count something for the total number of ways to count it. So if there's m ways, where m is some number, if there's m ways to um, count one item, and n as in Nancy ways to count a second item, then there's m times n ways to count them together. Good morning, Keegan. Glad you made it. We're just doing a review right now of what we left off with before the spring break, and then we'll do some of the problems from this mastery test together. And then I want to stop at 10:30, so that way you can work on it yourself. And I've got all the remaining questions ready to go, and I can help if you have any questions. So first thing to review was this fundamental counting principle. So this is not new. It's from before the break, but it's been, a week and a half since we've done this together. So the fundamental counting principle, this was like if we were making sandwiches and we had to pick one item from each column. Then we just multiply the total ways to pick each item together. So for instance, if we were picking like how many breads. Let's say there was 3 different breads to pick from. And then there's like 4 different meats to pick from. So then how many different different sandwiches could we make with the 3 different types of breads mixed together with the 4 different types of meats? It would be 3 times 4. 12 different total sandwiches that you can make with 3 different breads and 4 different meats. So we're going to rely on that fundamental accounting principle. And then we talked about the permutations and the combinations. Okay, so permutation, and we have a formula for each of these. This is how many different ways to pick a smaller group from a larger group, and the order of the picking matters. So think of permutations and combinations as an arrangement. How many ways are there to arrange items in a group? How many ways to pick or arrange a smaller group from a larger group? In our formula, the smaller group is R and the larger group is N. And here's the formula. So N pick R, N permutation R is N factorial over N minus R factorial. And let me add to our notes here. Order does matter for the permutations. The other one we had was a combination, and this is the same idea except order doesn't matter. So the order of the arrangement isn't important, but you're still picking a smaller group from the larger group. So picking R items from N. Smaller group R from the larger group N. The formula. It's the same as the permutation formula, except on the denominator in the bottom, there's an extra times R factorial. It's the same formula, except there's an extra R factorial on the bottom. And because there's that extra number on the bottom, or extra group of numbers that it's being divided by, it basically cuts it into a smaller number, cuts the top number smaller than it would be if it was a permutation. So here's the 3 things we did before break. And now I want to do some of the problems from the mastery test with you. Some of them are just finding the fundamental counting principle, like how many different ways are there to count the items. And then some of them are simply finding a permutation or a combination. But then there's more complex ones that I want to do with you. So let's start with this one. All right, just ahead of time, these questions are probably a little old-fashioned, because they rely a lot on gender, identifying people by girl or boy. So, forgive me for that. It's from our Edmentum. Honestly, it's pretty old fashioned, and it's going to take a while for math curriculums to kind of catch up and do statistics problems without relying so much on people's genders. So, anyways, there are 6 girls and 7 boys in a class. A team of 10 players is to be selected from the class. How many different combinations of players are possible? So, what's the larger group in this context? And what's the smaller group that we're picking in this context? Can you think about that and type your answer in the chat? There's a larger group of items here and a smaller group of items. So we need to start by identifying the larger and the smaller group that we're picking from the larger group. Any ideas? Can you type any of your thoughts or ideas on that in the chat? Larger group, smaller group. No ideas? Okay, start at the beginning again. There are 6 girls and 7 boys in the class. So how many people is that in the class right now? How many people total are in the class, girls and boys together? Okay, one person responded. Thank you. Keegan, awesome. Yeah, I know. Thank you, Keegan. And to everybody, yes, I was trying to break it down into maybe too simple of an idea. So you're thinking, why is he asking? But we have to start there. Thank you, Keegan. 13 people total. I'm going to put that here. And then it says a team of 10 is to be selected, picked, or taken from the class. So this is our smaller group. 10 players are going to be made into a team from the 13. So this is our larger group, and we're picking a group of 10 from the 13. This is our smaller group of 10. Because we have a larger group and we're taking a smaller group from it, that's a clue that we're doing either permutation or combination. They're asking us at the end how many different combinations. So they're kind of telling us we're doing a combination problem. Because there's no hierarchy here, there's no like ranking, like the first person is like the team leader or anything like that. It sounds like the order doesn't matter. Does not matter. So another clue that we're doing a combination, because remember, combination is like doing the same thing as a permutation, but order doesn't matter. So this is a simple combination question, problem, exercise. We want to know how many ways are there to pick 10 from 13. So 13 people, C, 10. 13 choose 10. So the first number is the larger number, the n, and the second one is the r number. So going back to your formula, it's going to be 13 factorial over 13 minus 10 factorial times, because this is a combination problem, another r factorial. So 10 factorial. So we'll simplify this. Let's simplify the denominator first. 13 take away 10 is 3. So we have 3 factorial times 10 factorial on the bottom. Now what I want to do is expand the factorials out and cancel whatever we can to make it easier and find our answer. So I'm going to, remember factorial means it's that number times all the integers below it. So 13 factorial on the top can be rewritten or expanded as 13 times 12 times 11 times 10 and so forth. I'm going to stop it at 10 because in the denominator we have a 10 factorial. And we can just cancel those right across each other. I'll expand out the 3 factorial as 3 times 2. Okay, now we can cancel anything that's a match on top and bottom. So we stopped the 13 factorial at 10. We could keep going and write it as 10, 9, 8, 7, 6, but the bottom is also 10, 9, 8, 7, 6. So we're going to cancel the 10 factorials right now. And then we can do some dividing, some reducing. We've got 3 times 2, that's 6. And 12 on the top over 6 reduces to 2. So there's the 2 from reducing 12 over 6, 12 divided by 6. So what's left here? 13 times 2 times 11. So this is telling us how many different arrangements we can make, picking 10, picking 10 people randomly from that total larger group of 13, where an order doesn't matter. 13 times 2 times 11. 286. $286 ways to pick 10 people from 13. Someone dropped off the call. Any questions right now on this exercise? Lois Bailey. Okay. Let's look at this one. Okay, here's a new question. Notice that the last question we did, it didn't ask us for a probability. It was only asking how many ways are there to pick. So in the last question, there wasn't a decimal or a percentage, right? It was just a straight up number. Well, now this is asking us about probability, so we'll get a decimal or a percentage answer. So we'll talk about that. Let's look at this from the beginning. You want to make 5-letter codes that use the letters A, F, E, R, and M without repeating any letter. What is the probability that a randomly chosen code starts with M and ends with E? So there's several things to keep in mind here. This is a probability question. So remember, it's going to be target over total. So we need to know what are the total number of 5-letter codes we can make without repeating. Using those 5 letters they gave us. Total number of 5-letter codes. No repeating the letters. So no like codes will have 2 A's or 2 F's or 2 R's or anything like that. And then we need to know on top of our probability how many of those codes have an M at the front and an E at the end. Start with M and end with E. Okay, so let's see. Let's see. So to find let's start with the denominator number. The total number of 5-letter codes, no repeating. So because it's without repeating any letter, and we're asking how many ways are there to arrange those 5 letters, this is essentially a fundamental counting principle question. We want to arrange A, F, E, R, M, all the different ways. So just to give you a visual idea, here's one way, A, F, E, R, M. Here's a second way, A, F, E, M, R. So we essentially want to know how many different arrangements of these 5 letters exist. So we're going to use permutation. However, we're not picking like 2 letters from the 5 or 3 letters from the 5, but we can still use the permutation or the fundamental counting principle to answer this. So as a permutation, it's 5 total, picking 5. How many ways are there to pick 5 from 5? So what happens when we plug this into the formula, n minus r, 5 minus 5, factorial on the bottom, that's 0 factorial, which is just the number 1. So we essentially are just doing 5 factorial, which is the fundamental counting principle, 5 times 4 times 3 times 2 times 1. So there's 120 different ways to arrange the 5 letters. This is our total number that will go in the denominator. Now for the target, how many of them specifically start with M and end with E? Here's where it's a little more tricky. So we want them to be in this format: M, 3 letters, and then E. So those other 3 letters are A, F, and R. So think about it this way: we're taking those remaining 3 letters, and we're going to we're basically asking how many different ways are there to arrange those 3: AFR, um, ARF, RAF, RFA, FAR, and FRA. So because it was just 3 things, we're able to make the list. We could also have just used the fundamental counting principle, arranging how many ways are there to arrange 3 items in a group, which is 3 factorial, which is 3 times 2, which is 6. And that's these 6 items here. So there's, for the probability to answer this question, starts with M, ends with E. Six over 120. There were 6 ways to have it start with M and end with E, and there's 120 ways total. So 6 divided by 120. 5% chance. All right, we've only gone over two of the example questions from the mastery test. I want to do one of the more complex ones with you, but before we do, would you like to see more of the same caliber that we just did, the last two examples, before we bump it up a notch? Any requests? Any thoughts? No. Okay. This one we should do together. So there's a couple problems in the mastery test that are going to be similar to this one. So I wanted to walk through this one with you guys. And if you get one that's like it, it'll be done the same way. From the beginning, a box contains 20 light bulbs, of which 5 are defective. If 4 light bulbs are picked from the box randomly, the probability that at most 2 of them are defective is what? In the box, there's 20 light bulbs. 5 of them are defective. So I'm gonna write those out. I'm gonna map out this problem from the beginning. We have 20 light bulbs, 5 bad ones, 5 defective. So I'm gonna write those as defective D. So here's our 5 defective light bulbs. And then I'm gonna write the other remaining light bulbs as G for good. Good. So here's our box with the 20 light bulbs in it. Now we're picking 4 from the box randomly. And we're asking what is the probability that at most 2 of them are defective. So if we pick 4 light bulbs from the box and we get 0 defective, that counts as a success. Or if we get 1 defective, that's a success. If we get 2 defective, that's still counted as a success. This is because we're asking the probability that at most 2 are defective. So I want you to think about this example like we were doing probability of 0 defective or probability of 1 defective or probability of 2 defective. Now, from our second day in probability, we learned about the OR questions. So this means we're going to be adding up those separate probabilities. We need to figure out the probability of picking 4 light bulbs out of the 20 and having 0 of them be defective. That's the first case. Picking 4 light bulbs and having 1 defective, second case, and then picking 4 light bulbs having 2 defective, that's the third case. And then we're going to add those 3 together to get our final answer. So let's look at the first case first. The probability of picking 4 and getting 0 defective. So we need to first ask, how many ways are there to pick 4 from 20? Four items from 20 with order not mattering. It doesn't it doesn't seem like it matters if what the first and last light bulb is, or first and second, third and fourth light bulb is. They're just a group, so order does not matter. So we use a combination. So we're going to say 20, choose 4. And this is figuring out how many ways are there to pick 4 from the 20. So that's n factorial over n minus r factorial times r factorial. So that's 20 factorial over 16 times 4 factorial. So we're going to expand the large ones until it reaches the size of the next one that you could cancel with it below. So I'm going to expand the 20 factorial until it reaches 16 factorial. And I guess I'm going to expand the 4 out as well. 4, 3, 2, 1, but I won't write the 1. Okay, so on the top of the fraction, we've got 16 factorial and on the bottom, so they cancel right away. Now we can do some simplifying here. 4 goes into 20 5 times, 20 over 4. So I'm going to cancel the 20 divided by 4 and replace it with a 5. 20 divided by 4 is 5. 3 times 2 in the denominator is 6, and 18 over 6 is 3. So 18 on top divided by 6 on the bottom gives me a 3 left over. So now we're left with 5 times 19 times 3 times 17. $4,845. 4,845. This is giving us the denominator of our probability. This is telling us how many ways are there to pick 4 items randomly from the 20. Okay, so we're going to use that. Now, let's see here. Picking 0 defective. Okay, so first we have to look at these 3 cases: picking 0 defectives, 1 defective, or 2 defectives. So below my red, let's start this in a different color so it's a little bit distinguishable. Let's try green. So now I want to figure out what is the probability of picking 4 items and having 0 of them defective. So this is a matter of a range of we're going to be using the fundamental counting principle and combinations at the same time. So in order to pick 0 defectives, that means I've picked 4 good ones. So we need to show using the fundamental counting principle, there's going to be so many ways to pick 0 defectives and so many ways to pick 4 good ones from this total above of 5 defectives and 15 good ones. So we're going to show 5 defectives, choosing 0 of them, and that gets multiplied to the good versions. There's 15 total good, and we want to pick 4 of those. So we have to do 2 different combinations, multiply them together, and that's going to be the numerator for this first probability that we're doing, probability of 0 defectives. In the past, people have said that it's cut off at the bottom. Can you guys see what I've written here? The 5 choose 0 times 15 choose 4? Or is that cut off for anybody? Keegan says yes. Okay, thanks, Keegan. If anyone is having it cut off, please tell me right away. Okay. And I want to label this. This first one I'm showing, this is picking 0 defective from 5 total defectives. And then the next one we have next to that, that's picking 4 good ones from the 15 total good. Why 4? Because in the problem it said that's how many we're taking. Up at the top in the writing, pick 4 from the 20 randomly. Pick 4 good from 15 good. Okay, so I'll work on this to the right of that. So for the first one, 5 choose 0. That's going to be 5 factorial over 5 minus 5. Factorial times r factorial, which is 5 again. Oh, no, I'm sorry. That's 0. 0. And next to it, and we'll work on these as we go, the 15 choose 4. This is picking 4 goods from 15 total goods. So this one's a little more interesting. 15 factorial. 15 minus 4 is 11 times 4 factorial. Okay. So the one on the left. This one is going to turn into like 1, I think. 5 factorial on the top over 5 minus 5 is 0 times the 0 next to it. So basically that whole denominator turns into 1, and we're left with 5 factorial, which is... Wait a minute. Did I do something wrong? I'm sorry. 1 second. No, that looks right. 1361. 1365. Yeah, these are supposed to be combinations. 1, 0. Oh, that's what I did wrong. It's okay. 5 minus 5 should be 5 minus 0. It's n minus r, 5 minus 0. There we go. So we end up with 5 factorial over 5 factorial, 1. Now for the one on the right, which is a little more interesting, 15 factorial. We expand that till it reaches 11. Because there's that 11 on the bottom, so we can cancel those. So that's why we stop there. And then we've got 4 factorial, which is 4 times 3 times 2. So 11 over 11 factorial can cancel. 4 times 3 is 12. So I'm going to cross out 4 times 3 and the 12 on top. And then 14 over 2 can turn into just plain 7. 14 over 2 is 7. What's left? 15 times 7 times 13. 1365. So what did we just find? This 1365 is randomly picking, it's how many ways there are to randomly pick a group of 4 items from this 16 and get 0 defective. Sorry, 4 from the 20 and getting 0 defectives. So the first probability, look again at the top, we're more in the center of the screen. I'm going to write it in red here. The probability of getting 0 defectives is 1365 over 4845. 4845. Remember in purple, we found 4845 right here. I just start it. That's how many ways to pick 4 from 20 total. So that's like target over total. 1365 over 4845. Target over total for just getting 0 defectives. So I'm going to have to go to another screen, and we need to do the same thing now for the second case, picking 1 defective and then picking 2 defective. And then we add them all up, and then we're finally done. This question is why I decided to wait till today, because I thought we might need more time for something like this. And obviously, we're not going to be able to stop and do our mastery test together. So I'm going to finish this problem with you so you see the whole thing worked out. Today, though, the homework is to try to do that very first, or not the very first, try to do the mastery test called using counting techniques to determine probabilities. Right here, using counting techniques to determine probabilities. And we will go ahead and finish this question. Where we left off. And then we'll probably be done for today. So next up, we got to find this middle probability of getting 1 defective. Probability of picking 4 things and getting 1 defective. So if we want to pick 4 items from the 20 and we have exactly 1 defective bulb, that's like we need to figure out how many ways are there to pick 1 from the 5 total defectives. So 5 choose 1. There we go. There's 5 defectives. We want to, and we have 1 bad one, times 15 goods, choose 3. So this on the left is picking one defective from 5 total. And then the second one I've written is picking 3 good ones from 15 total goods. There we go. So I'll do this to the right. The first combination is 5 choose 1. So that's 5 factorial over 5 minus 1, 4 factorial times 1 factorial. Expand the top one, 5 times 4 factorial, and I'm going to stop there because this time we have a 4 factorial in the bottom. 1 factorial is just a 1, so we can basically cross it out or cancel it right away. So 4 factorial over 4 factorial is 5 over 1, which is just 5. So there's 5 ways to randomly select one out of those 5. Now for the other one, 15 choose 3. 15 minus 3, remember it's n minus r, so 15 minus 3 is 12 times r factorial, which is 3. Expand the top till it reaches the next highest number in the problem. So 15, I'm going to expand it out to 12 factorial. And then we do want to expand the 3. So 3 times 2. Twelve factorial over 12 factorial cancels. Now, 14 over 2 can become 7. And 15 over 3 can become 5. So what's left? There's nothing else to cancel. 5 times 7 times 13. $455. So the one in the middle, the 5 that we got, that's how many ways there are to pick 1 from 5 defectives. And then on the right in purple, we finished that one in purple. That's how many ways there are to pick 3 from 15 goods. Remember, we have to multiply those together because this is analogous to like making the sandwiches. It's like how many ways are there to arrange the picking 1 bad defective and 3 good ones. So we're multiplying those together. We're basically doing fundamental counting principle with these 2 answers we just got. So we have 5 times 455, 2275. Okay, so what does that represent? It represents all the different ways we can pick 4 from 20 where only 1 is defective. Okay. Last up, we've got to do the third case, which is what is the probability of getting exactly 2 defectives? So this is going to be for picking the defectives. There's 5 defectives, choose 2, times the good ones. There's 15 goods, choose 2. Yes. So now we've got to write those both out. So I'll do those on the right where we have space. So for 5 choose 2, this is 5 factorial over 5 minus 2, 3 factorial times 2 factorial. That's n minus r times r. Expand 5 times 4 times 3 factorial. Three factorial over 3 factorial cancels. 4 over 2 can become a 2. 4 divided by 2 is 2. So this is 5 times 2, and that's 10. Now for the second part, 15, choose 2. This is the how many ways are there to pick 2 good ones from those 15. So what is that? 15 factorial over 13 factorial times 2 factorial. 15 times 14 times 13. 13 over 13, we'll just cancel those. 14 over 2 is 7 again. So 15 times 7. 105. Okay, now we combine these. Remember, we're multiplying these two combinations together. So 10 times 105. 1050. 1050. This is how many ways are there to pick 4 and get exactly 2. Defectives. Okay, so now this 3-part problem, we finally found all the parts. So we got 1365 out of 4845. Then for the finding one defective, we got 2275. And that's again over 4845. The 4845, remember, is total ways to pick 4 from 20. And then the last part we got was 1050 over 4845. Add those up, divide, and finally we get our answer. So 1365 plus 2275 plus 1050 is 4690 over 4845. Divide that for a decimal. Holy cow, we finally did it. So this is 0.968. So this is 96.8%. Or maybe they rounded up to 97%. So just a warning, there's a couple problems in the mastery test that are going to be like this one. How do we know if it's like this one? It's this keyword from the writing, at most 2. So because of that, we had to do 3 different cases. 0 defectives, 1 defective, and 2 defective. We don't do more than that because if we had picked 3 defectives, that's more than at most 2, right? It's greater than 2. So because of this at most 2, we basically know we have to do these 3 different ones and then add them all up. So please, today, do this mastery test. Give it a shot. I'm sorry we didn't do it as a group. Tomorrow, I want to move on to the new stuff with you, unless there's any questions from today's mastery test, in which case we can do a couple of those to start tomorrow. I've got your guys' attendance. So thank you for being here and taking notes, and I hope you're all doing well, and I'll see you tomorrow, okay?
Okay, bye.
Bye, Aaron. Andrew, Antonio, how are you guys doing on this so far? Any questions or concerns from today? Are you guys there? Can you hear me?